This lesson is for Mrs. Cucci's College Now PreCalculus class. We are picking up with lesson 4.1 where we left off, which I believe was about 1.18. Okay, so what we're going to do is we're going to take a look at the graph of f of x equals 2x minus 3 and the inverse of that function, which is x plus 3 divided by 2. We're going to use the same set of axes and we're going to compare the graphs. Okay, so what I'm going to do is I'm just going to insert a graph page. Type in my original function, which again was 2x minus 3. And then my inverse function, which was x plus 3 divided by 2. Okay, so if you take a look at these graphs, what you notice is this is actually a reflection. Okay, the inverse is simply a reflection over the line y equals x. Okay, and if you notice when I graph this, what happens here is they all intersect. Okay, what that shows is that it's a reflection. Each one is a reflection of the other over the line y equals x. All right, so again, the graph of f inverse is a reflection of the graph of f across the line y equals x. All right, so let's take a peek at x cubed plus 2. G of x equals x cubed plus 2. We're going to determine whether the function is one-to-one. If it is one-to-one, we're going to find a formula for its inverse, and then we're going to graph the function and its inverse. Okay, so the way we're going to start is by taking a look at the graph of the original function. Okay, so x cubed plus 2, I'm going to simply insert another graph page. X cubed plus 2. And we get this nice cubic function. Now, by looking at this, if we're thinking about a function being one-to-one, it's got to pass that vertical and horizontal line test, which in this case it absolutely does. Okay, I know that this piece of the graph right here looks like it evens out, but it doesn't. It is always increasing. And if you weren't sure of that, you could put a point on this and trace this out, but it is increasing on the entire interval. Okay, so since this function is one-to-one, what we're going to do is we're going to find the inverse of the function. Right? So g of x equals x cubed plus 2. Now to find the inverse, what we have to start by doing is start by switching x and y. So I'm going to replace that g of x with y. And then go ahead and switch those out. And now we need to solve for y. So we're going to start by taking this 2 and moving it over to the other side. So we get x minus 2 equals y cubed. And then we're going to take this y cubed and we want to make it just y. So in order to get rid of the y cubed, I need to take the cube root of each side. Okay. So we get y equals the cube root of x minus 2. And of course, we want to make sure that we write it in the right notation. The inverse of g of x equals the cube root of x minus 2. And there's our inverse. Okay. So the next thing I want to do is I want to go ahead and check this. Just do a partial check. And the way I do a partial check is by substituting a value in. So we start with my original function g of x. Let's say I want to find g of 3. We're going to evaluate the function at 3. We get 3 cubed plus 2, which is 27, plus 2, which is 29. Okay, so g of 3 is 29. Now, if I was right, if these two are inverses of one another, my next step should prove that. So what I'm going to do is I'm going to find g inverse of 29. And what I should get back is what I started with, which is 3. So the cube root of 29 minus 2, cube root of 27, which is 3. Okay, so since I got back what I started with, this does check, and they are inverses of one another. So my last step is to take a look at the graphs of these. Okay, so here's my original, and we said my inverse was the cube root of x minus 2. Now, if I'm correct, this should look like a reflection over the line y equals x. Okay, so I seem to be having a little bit of a glitch here with my calculator. But this is supposed to come down and then swoop back. I'm not sure why this doesn't want to play nicely with me right now. So it should look something like this. And then that would be a reflection over the line y equals x. Okay? And again, I'm sorry, I'm not sure why I'm not getting my complete graph here. Okay. So inverse functions and compositions. If a function f is 1 to 1, then f inverse is the unique function such that each of the following holds. F inverse of f of x is equal to f inverse of f of x, which is equal to x. Okay, for each x in the domain of f, and f of f inverse is also equal to x for each x in the domain of f inverse. So basically, what we're saying here is when we go through this and we take the composition of a function and its inverse, I should wind up with x at the end. Okay, so let's give that a shot. Okay, so we're going to see if this holds. F of x is 5x plus 8. And we want to show that these are inverse by using the composition. So f inverse of x is x minus 8 over 5. So we're going to do f inverse of f of x. Okay. So f of x is going to go into f inverse. So what that's going to look like is 5x plus 8 minus 8, right? It's going in for this value over 5. So this whole thing went in for x. Okay. This is equal to 5x over 5. 5's cancel and I'm left with x. Okay. Now the same thing should happen if I wanted to find f of f inverse of x. So going the opposite way now. 5 times x minus 8 over 5 plus 8. Those 5's cancel. I get x minus 8 plus 8. 8's cancel and I get x. Okay. So this does work. They are inverses of one another because I get this value, this x, at the end. Okay. Restricting a domain. So in the case in which the inverse of a function is not a function, the domain of the function can be restricted to allow the inverse to be a function. So what that means is we can take the domain of a function and only take a piece of the actual function so that its inverse is also going to be a function. So my first function, x squared minus 2, I'm going to take that and we're going to restrict its domain. Okay. All right, so by taking a look at this graph, I know that this right off the top of my head is a quadratic that's been shifted down 2 units. Okay? That you guys should be able to tell just by looking at it. So I know that this function, because it doesn't pass the horizontal line test, is not 1-to-1. And what that means is its inverse is not going to be a function. Okay? And I want its inverse to be a function. So what I'm going to do is I'm going to take this and I'm going to restrict its domain, meaning I'm only going to take a portion of this function in order to get a function for its inverse. Okay, so here's what I'm going to do. If I look at this function here, if I were to just take this piece here, this piece would be 1-to-1, meaning this piece, its inverse, would also be a function. Okay, so I could restrict the domain to be greater than 0, greater than or equal to 0. Okay, that would work for me, because then if I took this and I took the inverse would wind up being a function. So here's how we're going to look at this. We're going to take my original function, we're going to find the inverse. So we're going to add 2, and we're going to take the square root. And remember, when you take the square root, it's always plus and minus. Okay? So this isn't going to be the equation we're going to use. What we're going to look at is only using the values of x that are going to be greater than or equal to 0. Because we know from my original function that if I restricted that domain, then this will work for me. This will be a function. Okay? So what I can do is then I can build a table. So I want to start with my 0, of course. Okay, if I plug in 0, I get the square root of 2. If I plug in 1, I get the square root of 3. If I plug in 2, I get 2, right? Let's pick a value that works nice. We want another perfect square, right? 7, I get 3. So this would allow for a function that would give me a nice inverse. Even if I picked some, we're not going to use plus and minus because we don't want the negative one. Even if I picked -2, -2 plus 2 gives me 0. Okay, so we get this value of -2, 0, and we wind up with this function that looks something like this. Okay, and of course it's a reflection over the line y equals x. All right, so by restricting that domain, I was able to come up with an inverse that was also a function. So if we were to do the complete inverse, I know this is kind of confusing, guys. If we were to do the complete inverse, we would wind up with this other half. We don't want that because then it wouldn't be a function. So we only want the top half. All right, we're going to go over this a little bit more in class, but we're going to end here for today. All right, thanks, guys.